Neural networks. All right. So let's see where we are in our journey from no AI knowledge to practical AI knowledge. Up until now, we talked about how machine learning works, and in particular, these two broad categories of machine learning applications, which are regression and classification. And now we have enough foundation to move on to neural networks. And that's where the magic really begins. Let's review what we talked about so far. So we discussed that ML is about making predictions. And broadly speaking, there are two types of predictions you can make, or there are two types of values you can predict. There are continuous values like temperature, prices, or height or weight or duration. And those constitute the regression type of machine learning application. In contrast, we have classification type, which is about making prediction of discrete values, where there is a finite number of possible outputs that you can predict, like whether an email is a spam or not, whether an image is an image of a tree or a dog or a cat or something else. And these two are quite different in terms of what they're predicting, but they're actually very similar in how they work. And essentially, classification can be viewed as regression plus a squashing function that takes the output of your regression and squash it between 0 and 1. And it has to be between 0 and 1 because what you're trying to predict is the probability of the outcome being class 0 or class 1, right? But the way the learning algorithm work is almost identical. You have a loss function, you're trying to minimize it by following this gradient descent algorithm, which is iteratively tweaking the model parameters to minimize the loss. In other words, make the best predictions. The API for building this kind of model is almost identical as well, just as a refresher. So this is what you would do for linear regression to train and to make predictions with. And this is what you would do for logistic regression, which is actually the classification type of model. Now, don't worry about this naming of logistic regression being a classification type of problem, not a regression. But just to give you an idea of why it's called logistic regression when it's a classification problem. So logistic is a function that squashes the values between 0 and 1. And what it actually implies here is that you have a regression, a linear function, and then you apply logistic to it. But the point here is that when it comes to implementing it, there is very little that you have to change from one problem to another. And the code is very succinct, right? And now, like I said, that's where the magic begins. We're going to talk about neural networks. But let me set the context about what this neural network is, where it even fits into the story we said so far. So where it fits is that neural network is just another type of model. In the same light that you had regression, logistic regression, and decision trees and some others, you could have neural network. What that means is that this picture doesn't change. You still have training, you have inference. For training, you get examples with their input and output, and you build this mathematical expression, which is the model. And then you take that model during inference, you feed it the input, and then it will make a prediction of the correct output. And if you look at this picture of what training and inference of a housing price would look like, nothing changes here, except that the orange model on the right is going to be swapped from a linear regression with a neural network. So I hope that gives you an idea of where this neural network fits in. It's just another type of model. All right? And in a nutshell, A neural network is when you take, say, linear regression or logistic regression, these simple models that we talked about, you stack them up on top of each other and then you chain them together. So you will have this huge numbers of potentially huge number of small models or small operations that can together behave in a very intelligent way that you couldn't get with one linear regression or one logistic regression. So it's a layers upon layers of data transformation. And let me give you an analogy to bring that idea home. Say you want to make something in the kitchen. You have egg, you have broccoli, you have wheat. Well, you can get a blender and you can take certain amount of each, certain weight of each of these input, blend them together, and then make something. And for each of those input, you can take a different amount or different weight. And I'm going to show that with get rid of this weight and replace it with the thickness of these arrows. So the thickness of the arrow tells you like how much you're bringing in. And you'll make whatever you're interested in. Where it gets interesting is if you get a second blender and feed into it the same ingredients, but with its own set of weights, which are designated by green arrows here, right? And now you're making something quite different in the second blender because the weights are different. And now you can bring a third blender, take the outcome of the first and second blender, and then mix them in to have your final product. So this is not a perfect analogy of neural networks, but this is to illustrate the idea of stacking up and chaining simple operations. Here, the blender is a simple operation that takes a few inputs, creates one output, and by itself, it's not very flexible or very tunable. It's not too much it can do. But then once you get these different blenders and chain them together, now you can really create new things that you weren't able to before with one blender. In the world of neural networks, what we call here is, well, it's a network of 3 layers. So you have the input layer, you have the hidden layer, you have the output layer. Each of these blenders represents one unit of operation, which we call a neuron. And these connections are what constitute that network. And when you train the model, you're figuring out model parameters, which in this case, in the case of neural networks, are the weights. That's what you're trying to tweak. So the analogy is not perfect. What I want you to take away from this analogy is you can take simple operations, stack them up, and then chain them together to create some complicated solutions. But let's go back to this housing price, my favorite use case. On the left, the data set is the familiar data set. I just added some extra features. So you have the wealth or like the average household income. You have the area, you have number of bedrooms, and then you have price, which is what you're trying to predict. And let's build a neural network. What we have done so far was to create a linear regression model for this. And here is that linear regression that we talked about. The representation, the appearance is new, but the idea is what we talked about for a long time, which is you have these input values, x1, x2, x3, x4, x1 being area, x2 bedroom, x3 crime rate, x4 average household income. And then you feed them all into this one function that we call linear regression. And the output of this would be your prediction of the house price, which is W0 plus W1 x1 plus all the way through W4 x4. And the training of this model was about tweaking all these W's to get either most accurate estimates or the least loss. So this is the picture we're familiar with, right? Nothing new other than just the illustration of this. But if you were following the intuition about that blender situation, well, let's just draw the parallels with that blender picture. So here, this logistic regression, not logistic regression, but linear regression operation represents that blender. This is that one operation unit that takes different weights of these inputs, blend them together, give you one output. And up until now, I talked about W's as model parameters, which is what they are. But in the world of neural network, we like to call them weights. So if you hear weights, that means model parameters, same thing. And again, the arrows, the thickness here, I just tried to illustrate that. That means like W1 is large, W2 is large, W3 is very small, W4 is very small. And now, following the intuition that you just got from looking at that blender situation, you probably know where I'm going to go next. I'm going to add another unit of operation, another linear regression, and with its own set of parameters, with its own W0, W1, all the way to W4. So this W0 that feeds here wouldn't be the same that goes here, right? So essentially, here you have 10 parameters that your model needs to learn, not 5. Here you have 5, but here you have another 5. And just like we did for the blender picture, I will have another linear regression with its own set of parameters where the inputs to that are going to be the outputs of the prior neurons. Or I actually haven't introduced you to neurons, so the other units of operations. And this is a neural network with one hidden layer, one output layer, and one input layer. Let me see if I can turn on the pen. Yeah, and so this one has a total of 3 layers. Let's see how many learnable parameters the model has. In other words, when you do the gradient descent, when you're training the model, how many parameters should the model learn? Well, you have 5 here, right? You have 5 here for each of these weights, plus the intercept, which is W0. And then you have 3 here. You have 3 here because, well, it has its own W0, and then it has W1 for this, and it has a W2 for this. So total you have 13 learnable parameters. Yep, each of these circles or units of operations, we call them a neuron. And I will talk about why they're called neurons and why this is called neural networks. But the idea is actually pretty simple. You just stack up and chain these units of operations, which was linear regression or logistic regression. But magical things start happening. If you just think about what the picture I have here, let's say you initialize it with random W's, but after training you find that this neuron takes a lot of input from X1 and X2, meaning W1 and W2 are large and then the rest of them are small. And this one is taking large values, large W's from X3 and X4 and very little from everything else. So it could mean that what the model is learning here in these hidden layers, this one being a representation of the house size, because the number of bedrooms and the lot size could signify how big the actual house is. And this one could represent the school district or how good the school district is, because the crime is low, the average household income is high, And then what actually determines the house value in this output layer is a combination of the size of the house and the school district. Now, this, I was able to come up with a story of kind of try to explain what the hidden layer tried to learn. But imagine if you had 100 input neurons in the input layers and like a few hundred hidden neurons and a bunch of layers in between. There would be no way for me as a human to tell what the model is picking up. But suffice to say that because these neural networks are, they have so many learnable parameters in them, they are capable of picking up patterns that would be too complicated for a simple linear regression or a simple model to pick up on, right? So what I described had essentially one hidden layer, a couple of neurons, but this is more realistic what you see here. Here your input layer has 1, 2, 3, 4, 5, 6, 7, 8 neurons, and then you have 1, 2, 3 hidden layers and a bunch of output layers. Now, in the terminology of neural networks, we call this a deep neural network if there are a lot of hidden layers. And we call the wide neural network if there are a lot of neurons in a layer. So when you hear the term deep learning, what it's talking about is the training of a neural network that has a lot of hidden layers. So, but that terminology is kind of outdated, meaning that when they say deep learning, they mean neural network. When they say neural network, they mean deep learning. Because now the reason this terminology even exists is because when these things were introduced in 2012-ish or 2010, the compute power was so little, people had to use very small networks. So if you use a couple of hidden layers, suddenly they called it deep neural network. But nowadays, with abundance of compute, pretty much all neural networks are deep neural networks, right? Now, like I promised, I want to explain why it's called neural network, because you could have come up with a more boring name for it. You could have called it like the ensemble of simple operations, something that's more realistic and more accurate. But let me explain why. It turns out if you look at the neurons in human brain, this is what it's gonna looks like. So this is one neuron. This is another neuron. All right. There are electrical signals that are fed into the neuron from these branches that come in. You can see another one coming in. Another one is coming in here. They all come in. And then this neuron, kind of like the blender or like our linear regression or logistic regression, gets all of this aggregated and comes up with one value for the output, which is this. And then this feeds into another neuron. So just to draw the parallel, I'm going to go back here. If you think about this as one neuron, you see there are different inputs from other neurons that feed into it, and it creates one output that feeds into another neuron along with a whole bunch of others. And that's hence the terminology of neural networks. Next, why is it that deep learning is such a big deal? Because as we move on in this course, we'll be kind of exclusively talking about deep learning. So here's why it's a big deal. I want you to focus on the green line first. That is what traditional machine learning algorithms do. And by traditional, I mean linear regression, logistic regression, decision trees, and some others that have been around for decades. Horizontal axis is the amount of data that you have for training it. The vertical axis is the accuracy of your model, or how good it is, the performance of the model, right? And what it shows is that initially, the more data you feed into your traditional ML, the better the accuracy. But after a while, you reach that diminishing return, and the model doesn't get any better the more data you feed into it. And think about the housing price example. And imagine you're fitting a linear regression model to it. If I give you 100 data points, it's better than 10 data points or 20 data points. If I give you 1,000 data points, performance will be a little better than what you had with 100 data points. But beyond that, even if I give you 1 billion data points, that line that you fit to data is not going to move anymore. So because that line has already found its best fit with the first 1,000 data points. That's why, generally speaking, with these traditional machine learning models, the performance doesn't get better after a certain amount of data. What deep learning offers, however, is that red line is it can take advantage of excessive data. So the more data you feed into it, it can learn from it, it can accommodate for it, learn the pattern, and as a result has better and better performance. And this may not surprise you now because you understand with deep learning, you can quickly make it a lot more complicated. You can add a whole bunch of hidden layers and a whole bunch of neurons in each layer. And now, where with a linear regression model, you had only 10 parameters to tweak, with a deep learning model, you could have like 10,000 parameters to learn. And those 10,000 parameters are much more hungry for a lot more data than, let's say, 10 parameters were, right? So deep learning gives you, as the engineer, the ability to introduce a lot of complexities into your model, and that opens up door to take advantage of a lot of data. The final note I want to make here is, if you don't have much data, if you're in this zone from here to here, say, and in a lot of real life examples, that's where you'll actually be, then you will see that in many cases, the traditional ML algorithms outperform deep learning because, like I said, deep learning needs a lot of data to show its true magic. And that's where you may want to use traditional ML. So there is a place for deep learning and there is a place for traditional ML. And the place for traditional ML is when you actually don't have a whole lot of data. So, and with that, I'm going to give you a demo. So this demo is like a no-code UI provided by TensorFlow. It's called TensorFlow Playground. But let me walk you through this. So you get to choose whether you want classification or a regression problem. I want to stay with classification. Within classification, there are 4 data sets that you can choose from. Like, I can click on them so you can see what they're like on the right side. Here, let's look at this one. So what we have here is a bunch of data. There are 2 classes, like class 0, class 1, designated by different colors. So blues are one class, orange is another class. And we have 2 features, 2 input parameters, x1 on the horizontal axis, x1, x0 and x1. So you want to build a classification model that if you give it x1 and x2, any random values, it should be able to predict whether that data point is an orange or a blue. And I hope at this point it's clear what we're trying to accomplish, but think of that tumor classification where you wanted to decide if it's cancer or not. Say blue means cancer, orange means not cancer. And horizontal axis could be the diameter of the tumor, vertical axis could be the patient's age, something like that. Now, when it comes to the neural network, doesn't matter what it actually means. What you have are the 2 inputs. You want to make a prediction, right? And let me simplify it a little bit for you. Now, you get to design the neural net's architecture. I decided I want to have one hidden layer, which is this. In that hidden layer, I want to have two nodes, or two neurons rather. And then this is my input layer that has x1 and x2. And then this is the output neuron, which is just one neuron. And the values of it is going to be between 0 and 1. And then the dashed lines here represent the weights or the model parameters. And if you remember, I mentioned that with all this machine learning stuff, you initialize these parameters kind of random. Like right now, this is minus 0.13, this one is 0.24, it could be whatever. And the whole purpose of training is to tweak these parameters so the model makes the best predictions. Now with that, I'm going to start training and see what happens. I'm going to hit go. And I'm going to stop it right now. So we went 351 epochs or iterations. And what the model has figured out is that if your x1 and x2 fall into this blue region, it's going to predict it to be a blue. If it falls outside of it, it's going to predict the outcome to be orange. It's not a horrible classifier, but it's definitely not good. And this line, by the way, this like oblong V shape, is your decision boundary. If it worked better, the decision boundary should have looked circular going around this, but the model cannot, you can't figure out that boundary. And by the way, what you see here is this line. The horizontal axis is the time or iteration. The vertical axis is loss. It does show that the loss keeps dropping and dropping, but then at some point beyond that point, it just doesn't get better. What is the solution to this? How can we make it better? Well, the obvious one, in my opinion, is add another neuron. Let's make this model a little more complicated, a little more powerful. Right now, we weren't able to construct this decision boundary around the blue ones because your model didn't have enough parameters to tweak to really shape this thing. But let's see. I added one more neuron. I'm going to start training it. Look, how beautiful. After 111 iterations, it already figured out a decision boundary inside of which it's going to be one class, outside is going to be the other class. And that's pretty good, actually. And what is really neat is that it also shows you the parameters the model has learned. Look, for this weight, it's minus 1.8. This one, 1.7. This one, 1.8. So what that means is that it takes the output from this, multiplies by minus 1.8, feed it to this neuron here. This one, 1.7 times that output. This one, 1.8 times that. So now I want to show you a different data set. And this one, the data set is actually very nicely separated. And you can tell just a straight line should be able to separate the two classes, meaning a decision boundary that's just a simple line should work. And on that note, I'm going to get rid of any hidden layers, which means your neural net has only one neuron, that's the output neuron. And that essentially means you're back to this simple logistic regression, because a neuron by itself, or one unit of operation here, is that one simple model of logistic regression. And I think that should be enough to do the job, because I don't see much complexity in my data. Let me train it. And you can see it just very quickly found the line. How about this? I don't think with one neuron you will be able to figure out this, but let's just see it. As you can see, with one neuron, there is not enough flexibility in your model to construct a useful decision boundary. But what if I had like one hidden layer, two neurons? Much better. I'm gonna add one more neuron here, just add four. I'm just playing around, but you see, it's actually far better than before. So what I want you to do is play around with this one. This is a much more difficult decision boundary to figure out. Add hidden layers and the number of neurons. And also one other thing you can do is to introduce new features. It's true that these data sets have x1 and x2, but who said you can't engineer a new feature? Maybe you think that x1 squared would be useful to have, x2 squared, maybe x1, x2 would be a new feature you can add. Maybe the sine and cosine of these things, right? So the sky is the limit. If you want to really challenge the model to see how robust it is, you can start adding noise to your data. And the noise essentially adds blue dots where you usually have orange dots and vice versa. You can play around with the learning rate. The learning rate is how big the steps should be during training. And if you remember, you tweak the model parameters and how much you want to tweak it, very small or very large. And if you want, play with regression as well. But I hope this gives you some intuition about neural net.